Do you see my screen?
Yeah, we see it.
Okay.
Okay, so let me just introduce you briefly. So
Hello.
thanks.
Hello.
Now this is the right place. Yes.
What did you do to?
I checked the list of like participants, and there's a place that I found to call you, and I click there.
So to invite participant, to invite speaker, you have to do something manually. Okay. So I assume now I'm live, right?
Yeah, you're live now. Yes. So I think you can try to share. I will. I know, but I think you can share whatever you want to share.
Yeah.
And
it's strange that I hear myself like.
Yeah, it's replaying the old content for some reason. Okay, let's hope this stops.
So should I start now or?
Yeah, let me introduce you. Yeah, it's a pleasure. Thanks everyone for joining to this course that is part of the IGFAE academic training program. So it's a pleasure to have so many people connected. I see around 50. It's a pleasure to have Andre with us. We know Andre from our participation in the LHCb experiment at CERN, but Andre is a great expert with a lot of experience in this area, and he has worked for Yandex, that is one of the biggest companies in the world in the area of machine learning. So yeah, whenever you want. Thanks again for accepting being here.
Okay, thanks, Javier.
This is very inconvenient. Looping the what we said before for some reason.
Is that happening on somebody's side specifically, or in specific? Or is that just happening for everyone?
He's having some problems, so hope that we can solve it soon and we can start. It's like a second time I hear the same thing. Two events, teams, or third time. Classes. This one and the second one, which is for the exercises. Okay. Just wait a moment. I'm sorry for these problems.
So I try to mute, and even I might be on your side already, because I try to mute, and when I mute it, maybe what you can do is log out and log in again. I will call you the same way as before, just to be sure. So Andre, I think this is on your side because I muted you and then this stopped. So would you mind logging out and then logging in again?
Okay. Strange.
Apologies again.
No, do you hear me?
Yeah, we hear you.
Yes, I think the problem is gone now. So please, whenever you want.
Let me share my screen again. Do you see my screen?
Yep.
Yep.
Oh, do you hear me? It's replaying me again.
Yeah, we hear you. Yes, I think the problem is gone now. So please, whenever you want.
Okay. So hello everyone. Let me share my screen again. Oh no. Oh no. It's again repeating me. Do you see my screen?
Do you have headphones, maybe?
Yep. Yeah, well, but it doesn't depend on the headphones. So I hear myself speaking like a minute ago or several. Share my screen. No, it's again repeating me. Do you see my screen?
Do you have headphones, maybe?
So weird. Well, it doesn't depend on the headphones. So I hear myself speaking like a minute ago. I can mute everything and just start speaking.
Andrei, I think the problem is that you have the other, so you have the live event opened. So I think you have to close the other. I mean, you have to connect just as a administrator and not as a normal speaker. I think you have both things open at the same time. I think this is a problem.
Okay, so I've just closed the event window.
Yeah. Just let's leave it here.
Okay, good.
Thanks to Adrian for the tip. It was his idea. Yeah.
So just to make sure you see my screen and we're good to go.
Yes, everything is gone. It's going on now.
Okay.
So apologies everyone for the delay.
Once again, hello everyone, and thanks very much for organizers to invite me to this school. And within the next couple of hours, we're going to look at some interesting topics that would relate to machine intelligence and physics in particular. How does it apply? How you can start working with machine intelligence methods and tools. But before going to the details, let me spend just a few words on self-introduction. So I'm head of laboratory of methods for big data analysis at Higher School of Economics. So it is a place where Yandex has created a faculty of computer science. So Xavier was right mentioning that I was working for Yandex for quite some time. And I'm still head of LHCb team of Yandex School of Data Analysis. Now I'm more associated with Higher School of Economics, and on the right you see how it works quite closely. And so we are one team that work on the problems of machine learning algorithms and tools applied to natural sciences. So we collaborate with different institutions in the field of solving applied problems that probably can be improved with the help of machine intelligence tools. And also we're involved in education activities. We run summer schools, we run courses at universities, etc. And also we organize challenges that somehow bridge the gap between domain science, like physics, and machine learning. So I organized a challenge on Kaggle platform in 2015 and 2018. and each of those gives quite a bit of interesting insights into how algorithms can be applied to practical cases. Okay, so what we're going to look at today, as I mentioned, so a few examples of machine intelligence application for general science, for natural science, and then we go into deeper mode. So how actually those machine intelligence models are structured and built, starting from very simple approach of linear models. Then we'll look into figures of merit that can be used to estimate quality of those models, and some examples how one can shoot himself or herself in a foot, trying to find a bit more parameters than is needed, and how we can fix it using some mathematical approach. So, and it would conclude the theoretical part, and then we'll look into the practical notebook examples that will allow you to play and experience some of the methods described above yourself. Okay, so speaking of machine intelligence applications, there are plenty of those, but I selected several that seem to me most interesting. So they're ranging from computer playing game, especially a tough game called Go, defeating world champion Lee Sedol in 2014 or 15. Then understanding and generation of human readable understandable text, and recognition and generation of images that are indistinguishable from photos by naked eyes, and some applications of artificial intelligence to control things. So as Arthur Clarke mentioned, any sufficiently advanced technology is indistinguishable from magic, and to me, I think it truly is. But before going further, I would like to just spend a few words about artificial intelligence word itself. It is becoming inherently public once it hits a public media, and you can hear it from every microwave oven nowadays, and it is actually a very broad topic, and I would try to avoid using this term as much as possible, but in case you hear it from me, it most likely means machine learning. So machine learning is a very well-defined field that bridge the gap between data and between computational field of science. So it has methods and approaches and tools that we are going to look at today. And artificial intelligence is more like a myth that humanity has created or has been creating for ages, starting from ancient Greeks until recent examples. Well, maybe not recent, but well-known examples of Matrix and Terminator, right? So something in between mathematics and myth, there lies a more rigorous field of applications of mathematics to practical world examples, and I prefer to call it machine intelligence. So it's about terminology. So back to examples that I mentioned before. Here is a human written text on the left that has been fed to a machine learning tool that is called text generator, or GPT-2 developed by OpenAI, and you can see on the right what kind of text this model is able to generate. So I would not read it out loud, but if you follow it, it looks quite connected, quite nicely interlinked between different paragraphs. So the model is just learned by reading thousands of human written text and learning how different words connect to each other. And given the input of a word or a sentence, it can produce a few other words, and then it can reuse the generated words as a next step, next iteration input, and run endlessly. So this is just a big breakthrough that has happened a couple of years ago, and starting from this approach, people started to develop models that not only able to generate text but also to understand it. And here is a leaderboard of the level of machine text comprehension. So it is checked by asking several questions in natural language and correctness of the answers to those questions after the algorithm has read certain text. So, and you see on the first line of this table, there is a human participant or some baseline, and you see that machine intelligence algorithms and teams are getting very close to it. Another example is city street simulation that transforms a series of images that is captured by Street View Cam into a series of computer-generated images, so that it can generate arbitrary city escapes that would correspond to some physical simulation of a car riding across the city. Another example is quantum supremacy that has been announced last year. That is experimental confirmation that computations on quantum processors could be practically performed exponentially faster than on a regular supercomputer. So it is a work done by Google and published in Nature some time ago, like October last year. And there is not much of machine learning in itself, but if you think about the problem of controlling the state of 53 qubits, it is quite a challenging task. So a bit earlier, the same team has published a paper about using reinforcement learning to control those qubits, and they made a statement that with reinforcement learning, which is a quite prominent branch of machine learning, they can control qubits much better, much more accurate, and for much longer time. So I think the next iteration or next announcement of quantum supremacy quantum computation applied to more practical tasks would be with the help of these reinforcement learning techniques. So let us stay tuned for this. And here is another example that is more close to physics. It is a simulation of a physical interaction of particles. So it is a paper that is accompanied with some nicely laid out videos that I'm going to share. And just give me a second, please. I hope it will open in the proper window like this. So, and here it goes. So on the left, you see this water particle simulation performed by properly solved, properly written evolution equations, Navier-Stokes equations. And on the right, you see the same simulation performed by a neural network trained on a single step of evolution of those particles. And you see that the correspondence between left and right images is quite close. So and here you see how this water landscape is computed, that it consists of some particles that interact with each other and with the environment. And to be able to reproduce this water picture, you have just to estimate next position in time of those particles. Okay, so it is also quite a marvelous example how machine learning can be used to solve problems that previously can be accurately estimated only using supercomputers. Okay, so and before going to machine learning part, I also would like to spend or say a few words about the history of machine intelligence. It is a natural development of scientific history of our civilization. Sorry for too many bold words, but if you follow the shifts of big paradigms that are relevant to our civilization, starting from ancient Greek civilization that started to empirically explore surrounding world, building hypotheses about how does Earth work, how Sun spins around Earth, etc., collecting different facts about planets and trying to hypothesize about the nature of the planets and how they should be related to Earth, etc. And then followed by more theoretical approach, starting from Isaac Newton mainly, about giving a framework how you can compress significantly all amount of facts, all amount of knowledge that you have about the surrounding world into a very compact form of theoretical laws like a differentiable equation, like probabilistic theory, and other interesting stuff. So it gives another very important area of development with completely different laws of thinking, or about how science is going to develop, and it has given a lot of wonderful models that later on contributed to computational branch of science, allowing to compute the state of any given model using computer simulation. So, starting from mid of previous century, a lot of computational machines has been built to help estimate physical properties of very different phenomena. So, starting from fluid simulation, some climate simulation, also quite important, was to compute the outcome of such disastrous event as a nuclear or potential nuclear war, giving rise to the understanding so that we should not bomb each other, otherwise we end up in some post-apocalyptic winter. And but there are numerous simulators nowadays available, and it is completely different way of thinking how to compute an outcome of a system, outcome of the process, physical process, rather than inventing a law that would allow to estimate or predict the future state. That should be completely different. And now, after maybe 10 years or maybe 20 years of development, we see that the science is transforming again, and the most popular aspect of the science is kind of built on top of the previous two paradigms, on top of theoretical branch and computational branch, and it is pretty much data-driven. So data is captured by instruments and generated by simulators, and is processed by software, and some knowledge about those processes is stored in a computer in exchangeable form. So you can request information from a remote database like physics database or astronomy database, and use this data to do your own research. And for example, in astronomical science, doing a survey research is quite more popular than doing research by doing a single observation. And by survey, it means that telescopes has collected vast amount of data from different ranges of sky under different energy spectrum parts, and researchers are analyzing cross-correlation and some patterns observed by those telescopes. Okay, so, and now let me switch a bit, and I'm going to give you a few examples that are more relevant to physical science, particle physics especially. Yeah, here it go. Regarding physics, it is very special field machine learning, because you can recall many machine learning approaches that are inspired by physics process, like simulated annealing is optimization technique that is used quite frequently. It has been borrowed from physics. Markov chain Monte Carlo techniques is also quite popular approach for sampling random numbers from a given distribution, and it is also now quite popular technique. Or Gibbs sampling or Gaussian process, and just to mention a few. And this process is actually actively continuing, and I think that physicists here are in more privileged position, because many intuitions grasped by physicists can be transformed into one way or another into machine learning algorithms. And I would argue that most of the machine learning tools and most of the machine learning algorithms are just a conceptualized version of some learning techniques, and physicists use those techniques a lot on their daily basis. So there are many approaches has been converted, and there are many that has to be understood how to convert into a learning technique, and eventually all of the useful principles developed by physicists are going to be papers on machine learning, transformed by some clever postdocs or PhD students, or maybe by some of you. And speaking of application areas into of machine learning into particle physics, I would mention those 5 big fields. And it is a slide I've borrowed from Michael Kagan's talk. You will be able to follow the link as I share these slides with you. And there are those areas are range from data collection and simulation to testing of the hypothesis and performing a measurement. And so you see that as data is collected, they have to be reprocessed into a final state of the particles that describes relative position of individual objects and their types. And after that, you have to go into a high level abstraction, into event reconstruction and selection that would give you hints about what kind of collision has happened that resulted in a specific configuration of outcome particles. So, and finally, you go into a hypothesis testing and measurement that would allow you to refute certain hypotheses about the process that you observe with certain significance or not. And those are arrows that you see from left to right are examples of inference of some hidden or latent parameters estimation of the of different processes, ranging from low-level ones to a higher and higher level, and those are happening with the help of machine learning quite a lot. And another example that I would also to mention here is dealing with a very special case of the simulation of the events. So it is application of neural network to a simulation of outputs of certain parts of the detector. So it allows to condition on the properties of particle, like energy, momentum, type of particle, and generate the realistic output that would such a particle produce in given configuration of the detector. So to simulate this output, one has to use a special kind of neural network that is called GANs, or Generative Adversarial Network. Actually, there are many different kind of architectures that can be used for that task. But the idea is that neural network can do the simulation of the output of the detector in much faster way. So it is like 1,000 times faster, and the output looks quite realistic. So the biggest catch here is how realistic you want this output to be. And there are many measures and many discussions, maybe many papers that demand different aspects of this reality, of this realism, and then they train models to be more and more realistic. So, and speaking of modern challenges that are related to machine intelligence in physics, I would mention those ones. So, starting from the simpler way how to adapt algorithm developed by someone in the field of computer vision or natural language to the specific task that you faced in the physics field, or thinking how different data structures that exist in physics, like time projection chambers, like some emulsion detectors and other kinds of detectors, detector outputs can be mapped into techniques from the deep learning or from machine learning. Then how can machine learning help solve computationally costly problems like simulation or maybe some reconstruction problem? Or for example, LHCb is replacing one of the, so it is under consideration of replacing one of the triggers for online data processing into GPU-based architecture. And so the question to machine learning as well, how can one use machine learning algorithm efficiently on that architecture, on GPUs, etc., etc. And now you see these fields are quite actively developed, and if you want more details, you can follow the paper below. Okay, so now let's switch back to the question, to the slides that are more relevant to the learning part. So it is with this, I would like to conclude motivational part. And now let's look at this. So as we mentioned before, data-driven science and machine learning included has been around for quite a bit. And with this simplest approach that would help to look at machine learning is a function approximation. It is not the only one, not the maybe most fruitful approach, but it is most understandable one. So we start with claim that there is a distribution that generates certain kinds of instances independently. And we assume that there is a function, a known function, that maps those instances into responses. And usually instances are denoted by X and responses by Y. There are different classes of those responses. And machine learning starts with a question: how can we choose a plausible hypothesis that would map X into Y from a certain hypothesis space? And those hypothesis space is very important to choose. It is usually denotes a type of algorithm that you're going to use. So if you're going to talk about a linear regression model, so there will be a special hypothesis space for that. If you're talking about neural network, the hypothesis space will be different. It will be much bigger with much fancier components, but it still will be a hypothesis space. And another component that you have to identify before you start doing machine learning, it is a loss function, or the measure of the correctness of your particular hypothesis. And if we think about machine learning as a function approximator, the natural choice for such loss function would be a minimum square error. So we just see how different prediction of our model are from their ground truth. And if we minimize this quantity, it would mean that our hypothesis is quite close to the ground truth. Of course, there are many catches that we're going to touch, but it is a just general framework. Just an illustration. So we have some axes that represent air temperature. For example, you're constructing some kind of cooler or heater device, and you measure quantities like air temperature and energy output for this device, and you mark a blue dot as you make a recording. So the goal is to find the correspondence between xi and y and yi. Looking at this picture, it is quite easy to draw a line here by just without thinking about any math. A mathematical approach I mentioned on the previous slide would be a quite natural extension to this. So instances here are just blue dots. Responses are the energy output, so it is a quantity on the vertical axis, and hypothesis would be a line or some kind of a function that maps x into y, and the loss in that case would be the distance from the function we draw from the given instances that we have collected. Of course, it is just an approximation. So we just have a small sample of data, but it is we assume that it is as good as we can get, and we rely on this statistical distribution to build this function. That's why we look at just at the pixels, at individual hits. And learning in this example is would be finding parameters of this function. So we can assume that it is a linear function, and to plot a line, just a line into 2 dimensions, you have to specify 2 parameters. Right, one would be an inclination, and another would be interception. So you would just to find 2 numbers looking at this 20 or something dots. Of course, it is possible to find such a number. Okay, so we started looking at this one-dimensional or univariate linear regression. So we start with single feature regressor. Feature in the terminology of machine learning is very similar to variable in physics world. It just denotes some observable characteristic of our data that we have collected, or it could refer to some computed number. So it is not directly observed, but somehow computed. For example, on this case for air temperature, we can compute square of x, and we would have 2 features, x and square of x squared. That would be also possible to feed into a learning algorithm. But for the moment, we consider just a linear one. So dependent variable would be energy output, and we have a training sample. So those 20 blue dots, we will call it a training set, and we create a regression model that comes from this kind of equation. So we assume that there is a possible error of measurement that is denoted here by epsilon I, epsilon subscript I, and there is a hypothesis mapping that we can estimate, and this hypothesis is defined by this W. So parameters of the hypothesis here denoted by vector W. And for linear case, we see that this vector of W's is just two-dimensional vectors W1 and W0. So the goal of the training is just to find those two coefficients, W1 and W0. So looking at the numbers, you can see that you can plot those lines quite differently. Of course, the best one depends on the data that we have. So those lines differ by a subsample of those blue dots. As we mentioned before, the degree of quality usually is used mean squared error function that gives you the difference between predictions and the ground truth. So other measurements can be applied here as well. It's sometimes matter of taste, sometimes matter of computational efficiency, sometimes matter of physical interpretability. So there are plenty of metrics and statistics that has been around for hundreds of years, is full of those metrics. But the general idea, general guideline is would be able to choose that metrics that A is computationally efficient and B is relevant to the problem that you're trying to solve. We'll talk about computational efficiency a bit later. Okay, so if we plot, if we fix this measure to be mean squared error, so we have to find such W1 and such W0 that minimizes the difference, it would be something like this. And actually, you see that this problem is, it has more data that is needed. And of course, there is analytical solution available. So you can just substitute. So you can take a derivative of this function, and you know that if it is a convex function, then in the minimum point you have derivative equal to 0, and so you can solve this equation here, and the numbers, the notation here, mu x and mu y, is just a simplification or a mean value of x and mean value of y from our measurements. The same trick can be applied when you're talking about multidimensional cases. Of course, it is much more practical, but notation-wise, it is much easier to talk about not system of equations, but vector equation. So in our x vector would correspond to measurements in different observation, different features of different observation, different properties of observation, and W would be this matrix that we want to estimate, vector of coefficients. But essentially, it's not very different from univariate regression. So the problem for minimum squared error minimization is the following, and we can solve it again analytically by taking a derivative. But guess what? Computing analytic solution, which is the following, would be rather computationally expensive because you would have to transform a matrix, perform some huge matrix multiplication, inversion of matrix, and multiplication again. So it takes quite a bit of time when number of dimensions becomes more than you can afford. And then there is no need to perform this solution, find this solution analytically. There is a numerical the big branch of science that is called numerical methods, and stochastic optimization that can work for your problem. So if you consider optimization problem of minimization of certain function, in our case, it is the following, as mentioned on the right. One of the approaches that can be applied is called gradient descent. So you compute the derivatives of this function in every point with respect to every coordinate. So you can compute. And it is not a complicated thing, right? So looking at this function, if you want to compute a derivative with respect to W1, W2, it is quite a simple expression. So it is very easy to compute these derivatives. And then you would, for every point you want, you can compute a vector that goes into the highest increase of the function. And if you want to find a minimum, then we need to follow the opposite direction of the gradient from a given point. And the procedure starts from a random position in the space that we denote here as x0, and then we slightly move into direction opposite to the gradient. And here we have a coefficient that denotes how fast do we want to go. Let me here switch the screen again. Just to give you an illustration how it works and how it looks. Okay, so it is a part of online course that I have been working on recently. It is not fully complete, but at least it has some nice examples, including interactive examples, how this gradient descent work. So you see, you start from a random position, and then you compute the gradient with respect to the parameters of your model, and then you shift your position along those in opposite direction along the gradient. Depending on the speed of your on the coefficient that you choose, you may be traveling too slow or too fast. So it is very important to find a right number, a right speed for traveling. So, and here is the illustration how different points travel along the gradient line with different speeds. So I can choose a different function like this, and you see that the traces of those lines, traces of those points converge to the a minimum in quite a different way. And here is the illustration, two-dimensional case. So starting from different positions, you end up in the minimum or maximum, it doesn't matter. So here is a weird function, and you see that there are different kinds of points here. So there are minimums and there are valleys, and you can travel along those valleys quite a long time before you converge to a minimum. So you have to you intend to push those green dots a bit, because you see by your eye that, okay, there is a there is a slope, but the slope is very flat, and it takes them quite a bit of time to get to the final destination. That's why there are many techniques that we are going to look at maybe day after tomorrow, how you can nudge those green dots. But for now, you can just contemplate that in the different configuration spaces, you can go to optimal position just by computing the gradient and going down this gradient. And there is a mathematical statement that for smooth and convex functions with a single minimum, k steps of gradient descent achieve accuracy of O1 over k. So it is quite a bit of reassuring statement. So another approach not completely another approach, but approach that would allow to simplify computation even further. It is called a stochastic gradient that would be more efficient for large sample. Because in the original version of the gradient descent, you would have to compute the error with respect to the parameters for all data that you have. But if you want to compute it, if you have 10,000 or millions points, the computation of the gradient would be too slow. Instead, you could compute it for a single element, for a single observation, and then move along the gradient, and then repeat it for all observations you have. And in that case, the gradient that you compute would be very different, or well, not completely different, but different from the gradient that you compute with respect to the whole sample. Right, so here is the illustration. So with the gradient descent, you would move by those black dots. And if you apply stochastic gradient approach, so computing by one point, by another point, by another point, you see it would take much more steps before you achieve high accuracy. But it is much cheaper computationally. Okay, so let's take a look at animation. Sorry, animation would be in the practical part. This PDF is not playing it. This PDF player is not playing this animation. But again, I will show it to you later. So by training a model, you would see that this red line aligns itself with the blue dots. Okay, so let's go a little bit further. We looked at the way how you can solve regression problem. I mean, when you want to understand what is the best value of some parameters given observations. And now we take a look at the classification problem. So in this case, you want to know what class of objects has certain features. Or in more mathematical sense, you have a mapping between features and labels. So for binary classification, you have just two labels, -1, +1, or 0 and 1. It's up to method how to encode the class more accurately. So for some methods, it is easier to have it encoded -1 and +1. For some methods, it's easier to have it encoded as 0 and 1. But it doesn't matter much. So the goal is to find the mapping between features and those class. So just a simple example could be a particle identification for binary detector. For example, if you want to discriminate between muons and electrons, you encode electrons as 0 and muons as 1. But you can think of many more examples yourself. Here is an illustration for two-dimensional case. So you have two features, and the height of the function would correspond. Height of the function would correspond to the class that you want to detect. And the classification also can be stated as a machine learning problem, and also we have to pick a hypothesis space. And also we have to pick a matrix that would give us intuition about how good we are in our classification. And unlike previous example, when we wanted to estimate the distance, in that case, in this approach, we're going to estimate the risk, or the probability of failure along the samples that we have. So we shift from the one approach that is called maximum likelihood estimator to another approach that is a bit different, but for without going into much theory, the difference here is that we now computing probabilities. So let's consider a case for linear models. So we want to compute the linear model that would discriminate blue dots from red dots. And if we encode blue and red as a +1 and -1, so we can just draw a line, draw a straight line, straight because it is a linear model between those, and discriminate everything that lies on one side from everything that lies on another side by a sine function. And training a model would be finding parameters of this W function, and we can rewrite our loss function in the following term. And once we have this at our hands, once we have this function, we could hope to use gradient descent. But the problem is that it is a step function, and either the gradient of this function either flat, so it has zero gradient, or it is non-computable, so it equals to infinity. And it's impossible to optimize. The solution to this optimization problem, how to approach this, we introduce the upper bound for this function, and the upper bound can be as smooth as we want, and we optimize with respect to this upper bound, and then here are examples that we can use. So this red line here is a step function that was introduced by initial problem, and different colored lines show how you can draw the upper bound with respect to this step function. Those are smooth, and they depend on the inclination at different with respect to different axes. So depending on the fact how far you go from the how far you are from the optimal configuration from zero, they depend on the speed of convergence. So it is essentially correspond to the slope of the surface that we are going to travel to get to the optimal configuration. So logistic regression is stated in the following way. So we have probability. We seek for algorithm that gives the probability of the instance correctly classified, and probability of such an instance would correspond to the following term. So it is either prediction of our output of our model, given that the class is positive, or 1 minus output of our model, given the class is negative. And then we can write the entire likelihood for the hypothesis. Sorry, for entire set of our data, likelihood of our hypothesis. That will be multiplication of all probabilities for all points in our data set, right? And it is easier from computational perspective to rewrite it in log likelihood form, which is a negative, which we can rewrite as a negative log loss, but instead of computing multiplication, we have to compute the sum of those probabilities. And then the natural step would be to optimize this this loss function with respect to some age parameters that define the age. And one of the example of how you can define this age is a sigmoid function over linear model that we considered before. So this WTX is a linear model, and we take a nonlinear function, sigmoid function, that is depicted on the right here. So you can see that no matter what x we have, no matter what value we get for x, we do not get out of the 0, 1 boundary. And if we substitute this h, which is written here, 1 over 1 plus exponent negative wtx, to the equation here, and then you take a derivative, you can solve this problem in a pretty much similar way as we did before with just a linear model. And here is example of logistic regression on two-dimensional space. So we have x1, x2, two features, and color denotes here the height of the function. And the correctness of classification is also can be seen from this picture by your eye. Okay, so this is how logistic regression works. So we see it is a simple extension of linear model, and we can solve it using gradient descent or stochastic gradient descent. And now we have to understand, okay, we solved this. So we found some kind of approximation. How can we assess it? How good is it? And usually loss function is something that you can give to computer. But in reality, you also want to compute some properties of output of this optimization problem, output of these computations. And what you're usually interested in, at least in terms of classification, is the error rate for misclassification, positive as negative and negative as positive. So one of the simple metric here is accuracy. So if we have our hypothesis that outputs some real values from 0 to 1, and we fix some threshold t, some hyperparameter, so everything that goes above this threshold would be considered as a positive example. Everything that is below this threshold would be considered as a negative example. So it is this bracket notation. And then the accuracy would be the number of correctly guessed classes. So exactly in this. If we take an example, a Higgs challenge that has been published on Kaggle in 2014 or so, so there were quite a bit of background events and quite less number of signal events, like 1/3 of the whole sample consists of signal events. And the more informative representation of the error is the following. So instead of computing just a single number, you could compute for every threshold how many true positive numbers, true positive instances you have, true negative, false positive, and false negative. All right, so it's easy to compute these metrics, but comparing matrices is not very handy. Instead, you can introduce additional numbers that are false positive rate. That is a fraction of false positive with respect to sum of false positive sorry, false positive and true negative. So it is how many negative examples you have in your whole sample, and true positive rate. That is fraction of true positive with respect to true positive and false negative. So it is a fraction of true positive in your positive samples. And accuracy can be expressed in the following equation, right? But also remember that this table it depends on this hyperparameter threshold, and it will be interesting to see how it depends on the different values of this threshold. To compute this, to estimate this, we can compute those two numbers, true positive rate and false positive rate, for different thresholds. And we just make a plot that would that we get after we do this exercise. So it would look in the following way. So imagine you have a distribution of true negative, these blue guys, true positive, these red guys, and you have a classifier that separates blue from red. So it is a vertical line that somehow says that everything on the right is positive, everything on the left is negative. And then you can compute the confusion matrix here. And for every point that correspond to position of this threshold, you can estimate those two numbers, true positive and false positive rates. And you get dots that align along the curve, sitting somewhere here. So intuitively, if you can separate those blue and red dots distributions completely, so there is no overlap. So ranging, so the ideal ROC curve would look just like square. So it rises from 0 to 1, 100%, and then goes to the right. So it fills in this space completely. Oops. Sorry. I wonder if I can draw here. I guess I should be able to. Yeah, so ideal ROC curve looks like the following. But of course, if you're not separating those ideally, it would look something like this. And still, you got a plot. You can compute the area under this plot, area under this curve. So everything that goes here, and intuitively it gives you the higher this number, the better your classifier is. All right, and ideal classifier would have area under ROC curve equal to 1, and the worst classifier ever, random number classifier, would give value 0.5. So because you will not be able to distinguish good from bad, and it means that with increase of the size of the sample, you get as big number of positive examples, as bigger number of positive examples as bigger number of negative examples. So it would look like a diagonal here. Okay, and now let's move a bit further. So one property of this classification measure of figure of merit is that it works nicely for balanced data set, but if you have larger population of one class than another, then you might this quantity might be misleading. So let's look at the much higher misbalanced example. So if you have 1,000 samples and you have 950 background noise and 50 signal examples. Even if your classifier is trivial, like says everything equals to -1, so accuracy would be 95%, because we have 95% of our sample is a negative, so we would be accurate in 95% cases. And criteria that are better suited for imbalanced problem are the following. So you can just look at precision and recall properties, or you can introduce some artificial weighting. So you instead of computing true positive, counting every observation, every instance, every observation as individual, you could assign certain weight number to every sample and make weights of signal and background equal to each other. Okay, so another important thing is overfitting. So we can look at how easy you can fool yourself with simple linear regression. So let's take a look at the example of linear regression. And here we also introduce one important term. It is called generalization. So our loss function says how good we are on the training sample that we have seen. But of course, we're interested in the cases where we haven't seen during the training. Because for training, we know everything. For training sample, we know all the classes and all the features. But we're interested how well our model would perform on the data that has been around out there, that have to be yet collected, maybe. And generalization is an estimation of the performance of our model on new instances as well. And it is very difficult to assess quality or assess something on the data that we have not collected yet. So the idea is that we can have the data set that we use for training and the data set that we would use for testing our model. So let's see a simple example. So we have a one-dimensional case, and the ground truth of this case would be a cosine function with some noise, and we would have one original feature. And in addition to this, we consider two other cases when we have 4 features, just x squared, x cubed, and x to the 4th, and 15 features. Let's see how well the regression model performs in those cases. So it is called polynomial fit or polynomial regression. You see, for one-dimensional case, for linear regression, we have just a line that sits here. It doesn't describe nicely all the dots we have. If you look on the right, you would see that we managed to almost completely accurately describe all the blue dots with the blue line. But at the same time, here, MSE that is computed as a distance between green line and blue line is enormous. So it doesn't doesn't reflect the behavior of green line at all. And the best solution for our case sits in the middle. So we have quite close correlation between blue and green lines, and mean squared error here is quite small. So how to assess the quality of the model? As mentioned before, we just speak. We just take a special data set that we do not use during the training. So we have original data set, we pick part of it for training, and the rest take away and use for validation of the quality. And quality function is computed on this validation set. The problem with this approach is that this validation data set would be might expensive. So if we spend certain amount of time on collecting the whole data, half of this data like costs half of all the money, and there are much smarter approaches that allow you to use the whole collected data and still be able to estimate the generalization error of our model. So it is illustration how it works in simple case, and a more complicated case is called cross-validation, when we split the data into k folds of equal size, and we train the model on so for every k small, we train it on all samples but xk, and assess the quality of the whole model as an average of the qualities that we get of those subfolds. So here is the illustration. So we get 10 folds and train the model on 9 folds and test it on 1 fold. And the same here, but the folds are different. And we get some estimation of errors here depicted on the right, and then take the average. And this would give us an estimation of the error, and also it would give us the confidence interval or some distribution of those errors, which is very good. So you would understand if you have 91, it's like 91 plus minus 10 or 91 plus minus 1. So the training and testing model on k faults would also give you quite important information about your model. So comparing many faults to small number of faults, it's quite trivial. So for many faults, you have a smaller bias, so you would have all the models having roughly the same estimate around the true accuracy, but it would have large variance due to small fault sizes. And also it is quite costly because you would have to run many training of the same model many times. And with few faults, you would have quite the opposite. So it is a matter of a trade-off between computation and realisticity of estimation. And to deal with overfitting, quite interesting approach, mathematical approach has been introduced, and it's also quite intuitive one. So if you compute analytical solution for regression problem here, and compute those matrices. So if X would be equal to diagonal matrix with some eigenbasis of X, then it would mean that our solution would have huge diagonal values in this matrix. And to avoid this, we can add something to a loss function that we optimize for the gradient descent. So we add some kind of penalty that would restrict us from getting too large numbers of representing coefficients. So one can express it in the following terms. So you add regularizer over weights of the matrix with some coefficient that is called regularization constant. So the simplest way how to do this regularization is just to compute the sum of squares of those coefficients, right? So and the whole minimization, probably the whole minimization function that you have to find minimum of would be equal to the whole, and you still would be able to compute the gradient here. It is not very much more computationally expensive. There are other ways how you can regularize the function. So you can also compute the L1 norm. So it is called lasso regularization, or you can add two norms together. So it would be sum of those two. It is called elastic net regression. It's mostly a matter of choice, and the illustration how those regularizers work is the following. So imagine you're sitting here, so in this red dot, right? And you want to get to the optimum in your configuration space. If you add regularizers L1, so it means that you tend to sit on the axis. So it means that if we compute the gradient, it will not be going into this direction. It will be going into this direction. So the path would be a little bit different, and the coefficients that you get would tend to sit on the axis, and it means that you would have a lot of zeros or many zeros in your matrix of your regression, of weights of your regression, and that's why L1 norm is called sparsity inducing matrix. And for L2 it doesn't matter, so direction is not important, so you just go as you would go, but avoiding extra big numbers in the coefficients. And combination of those it gives you something like this. Okay. So another interpretation of regularizers. So it allows you to think of the gradients of, think of the weights to be changing in certain directions much easier than in other directions. So it brings me to conclusion of this lecture. So we looked at linear models that work nicely both for regression, and with some additions it can work for classification. Optimization tools that can be helpful and save a lot of computations are numerical and stochastic optimization based on gradient descent. Picking figures of merit allow you to give ideas about the problem that you're going to solve. And it is very important to choose how well does your model overfits. One of the helpful technique for that is cross-validation that is able to assess quality of generalization error of your model. And another one is regularization that really helps fighting overfitting. Okay, so this is it I wanted to cover in theoretical part. So what would be the next steps? Questions and then a break and then practical part, or how is it going to work now?
Thank you, Andre. Yeah, I think it's if there are questions, I think we could have some now. So you can write in the chat window on the right-hand side if you have any questions, and we will make them public. If there are no questions, yeah, as you said, maybe we can have a 20 minutes break, and then we come back to the other room. So for the hands-on part, people can speak directly. So maybe wait 1 minute to see if someone writes a question. If not, we have the break now. in the meantime, maybe we can try to write in the chat. Jose, maybe you can try to write the link to the other room where we will be meeting afterwards for the hands-on session. So it should be this one, if I'm not wrong. So, okay, if there are no questions, maybe we'll reconvene. So it's 5 to 10. We'll reconvene at 10:15, as hace cuarto, in this other room here. So there you will be able to speak and to interact. So if some of you has issues connecting to this other room, let's send us an email, and we will try to add you individually. Okay. So thanks again. We meet in 20 minutes from now.
Okay, thank you.
Okay.
See you then.
See you then.